Okie dokie, I'm going to try and get through questions 7 and 8 in one go. Right, so this is the electrochemistry question. Not very easy, I think, but fairly routine. That they are typically a bit tricky. So the first question you have to work out is the balanced overall equation when you combine two half cells. You can't just pick the reaction at random. You have to think about it a little bit. So first thing to note is for every reaction you are going to get both an oxidation and a reduction. So one of the reactions from up here is going to be going in the forward direction, one of them is going to go in the reverse reaction. Okay, reverse is oxidation, forward is reduction. Okay. Now we're comparing here nickel and iodine half cells to start with. Out of those two, the iodine to iodide reaction is the most positive. That's the one that kind of wants to go in the forward direction the most out of those two. So that does. And therefore the other one goes in the opposite direction. Okay. So you combine those two together, nickel and iodine. So nickel going in the backwards direction, iodine going in the forward direction, goes to iodide and nickel 2+. You should have cancelled out any electrons there. So most people got that right. I think that should be okay. Some of you also wrote out the half equations, then combined them. You didn't really need to. You could probably do that in your head. Predict, giving a reason, the direction of the movement of electrons when the standard nickel and manganese half cells are connected. Well, this time we're comparing the top two, this one and this one. And this time, nickel's the more positive one. So I'm not sort of embarrassed to show you my thinking here. There's so many conventions and things to remember with this. I just kind of sketched out. I might have done it with a shorthand notation, but kind of in reality. But I thought I'd just quickly sketch out the two half cells combined, like I would have done in class. We know that the oxidation is on the left, ox red. Remember, we taught you ox red. The most negative one, which we sometimes call the most reactive, but most negative one on the left-hand side, most positive one on the right-hand side. Reduction on the right, oxidation on the left. And we know if we set it up like that, the electrons go in the clockwise direction and we get a positive voltage. Okay, so if you combine this, set this up properly with a positive voltage, the nickel's on the right, manganese is on the left, so the electrons must go, can't get in here, from manganese to nickel. Okay, all you have to say is 2 nickel there, really. And the reason why is because the nickel was the one with the most positive E standard for the half cell, or you could have said that the manganese is the better reducing agent. It doesn't matter exactly how you word it, but you refer to the electropotentials in the explanation there. Okay, and I'll add that when I photocopy up these notes for you. And then the next one, you've got to combine two different half cells. So you've got to compare now iodine and the manganese. If you look up those numbers, I've scribbled it down here anyway, but if you look up those numbers, the manganese is the more negative half cell, or E standard for the half cell, and the iodine is the more positive one. So again, that's the one that would be on the right hand side if it's set up properly, and this is the one that would be on the left hand side if it's set up properly. Okay, you can think about this in a whole bunch of different ways. But you know, don't you, how to do that sum? I haven't got the answer in front of me. But the E cell is equal to the right hand side, which is plus 0.54. Take away the left hand side, which is minus 1.18. Okay. And that gives you a value which you'd have to quickly look up because I haven't written it down. Okay, and that number has magically appeared. It's plus 1.72 volts. I don't know why I couldn't do that in my head. The other way to think about this is that E standard equals the reduction process, take away the oxidation process. You can do it in a whole bunch of different ways, but I've tried to stick with the way that I've taught you. Loads of ways of people work these out in different ways. The last thing to do is to work out the best reducing agent in the table above. Okay, so let's have a look at the table above then. There are 6 possibilities: either iodide, nickel, manganese, Mn2 plus, Ni2 plus, or iodine. It had to be one of those. So you can't give two things. You can't give a whole reaction. Say it's that one. It had to be one of the species, one of the things out of those 6. Okay, so to start with, it had to be a reducing agent, which means it itself must get oxidized when it reacts. So that means it must be one of the substances on the right-hand side. It has to be either manganese, nickel, or iodide. Okay, so anyone that put any of those 3 had no chance of getting a mark. So which of these 3 is the easiest to oxidize? In other words, which one's got the reaction which goes to the left-hand side most favourably? Well, it's the one with the most negative E standards for that half cell. So it must be manganese is the answer there. Actually, most people got that right. We spent a bit of time on that in class, and I was quite pleased that most people got that right. So well done. That's the electrochemistry one. Electrochemistry is, I think it's pretty hard. I think it's the hardest, one of the hardest topics. And you know, you're gonna have to work at it as you study for the electrochemistry test we're going to do, or the redox test we're going to do in a few weeks' time. Let's sort of finish off with a bit of fun, a bit of organic chemistry, nice and easy. So you have to deduce the type of chemical reaction and the reagents used to distinguish these 2 compounds. At this point you pause, you breathe, you have a think, you have a look. What functional groups have I got? Okay, I've got a hydroxyl, if you like, or you could argue it's you can call it a secondary alcohol, which it's a carboxylic acid, and over here you've got a carboxylic acid again, and you've got a hydroxyl, or prefer to call it a tertiary alcohol. Right. So now you know you've got a secondary alcohol here, and a tertiary alcohol here. You know how to distinguish them, and it's not with bromine water, which most of you put. Bromine water is to test if you've got a double bond, a carbon-carbon double bond, an alkene, which alkenes decolorize bromine. But if you want to compare these 2, you can do an oxidation reaction. And if you do that with potassium and dichromate in the presence of acid, usually sulfuric acid, or just say acidified potassium dichromate, job done. Okay, and that's all you have to do for that question there. Let's see if I can keep that there when I bring up the next question. Okay, so there's the 2 reactants again. What would you expect to... you're not going to be able to see it, are you? That. What would you expect to see for each of them? So for the secondary alcohol, you'd expect to see a colour change. So potassium dichromate is orange. It's oxidation number 6. It's an orange compound. Really nice to do these practicals in the lab, wouldn't it? Maybe that's a good idea for something we should do. In time, I haven't done much practical work this year, which I regret. When you react it with acidified potassium dichromate, as long as you don't have too much dichromate in there, the dichromate should go green, which is now chromium 3+. So this is the dichromate, which is in oxidation state 6. Okay, it's orange, that's green, and compound B doesn't react, so no change, it stays orange. Right, what about the NMR signals? Okay, now, I was surprised that you didn't do a little bit better on this one. We did quite a lot of practice of NMR. Some of you did it, some of you just forgot those basics. So you have to count the number of signals. The trick is with this is to spot equivalent signals. Okay, so let's just count them. So these hydrogens here and these hydrogens here are equivalent. So we'll call those set 1. This one here is unique, call that set 2. This one here is unique, 3. This one here is unique, 4. This one here is unique, 5. Okay, so there's five signals for that one, and the ratio is 6 of the first type, then 1 of all the others. 1, 1, 1, 1. Let's get it right. 1, 2, 3, 4. 1, 1, 1. 1, 1, 1. There we are. So that's the first one. So 2 marks for that. Tick, tick. The second one, just like before, that and that are the same as each other. So it's set 1. This one's unique, set 2. These two are the same as each other. We'll call that set 3 or set C. And this is unique. So it's four signals, and they are in a 6 to 2 to 1 to 1 ratio. 6 of those, 2 of those, 1 of those, and 1 of those. 4 marks for that. And which one can show optical activity? So for that, you're looking for a carbon. So one of them's definitely got a carbon with 4 different groups coming off it. I'm going to go straight to the right answer, which is this carbon here, because it's got a carboxylic acid coming off here. You can't see. This carbon here is a chiral carbon, so sometimes you're asked to label it with an asterisk or something. It's got 4 different groups coming off it. It's got a COOH coming off it, it's got hydrogen coming off it, it's got OH coming off it, and it's got this chain coming off it here. So that is, the answer is compound A, because it's got a chiral, A has a chiral carbon. Or you could have described it by saying A's got a carbon with 4 different groups coming off it, I guess, as well. That's that one. Draw the 3-dimensional representation of the 2 enantiomers. Okay, I know this is something that's tricky, but it's quite common. It's only worth a mark, but it's worth a little bit of practice because it does come up quite a lot. You just start by drawing. The carbon that's chiral first, and then draw 4 groups coming off it at 120 degrees from each other, and then 2 more, both kind of over in the other position. 1 coming forward and 1 going back, like so. You practice drawing that, and it just doesn't really matter what you do after that. You just strap the other things to it. So we'll stick a COOH to it there. Put the C, that's that carbon. H, that's that hydrogen, and then 2 CH3s, and then the OH. Make sure when you draw an OH, particularly when you draw it backwards, the carbon is connected to the oxygen. We don't write H, or don't write OH that way round. And that's the other hydrogen, that one there. Okay. Then you draw a mirror image of it, is the best way to do it. Some of you did the trick where you just switch 2 of them to the position of 2 of them. That's okay. I like to draw a mirror image. Doesn't really matter. So that's the mirror image of it. But as I said, you could have drawn the same thing again, but just flipped the position of 2 of them. Now this next question is the free radical mechanism for ethane and bromine in the presence of sunlight. I think almost without exception you got 4 marks there, apart from the odd slip. I'm kind of reluctant to sit and draw it out now and make you watch me draw it because so many of you got it right. It's absolutely routine, it's absolutely straight from the textbook, notes, revision guides, everything. First mark for initiation, 2 marks for the 2 propagation steps, and 1 mark for any termination step. So forgive me for not drawing that out. I'll put it on the notes when I photocopy them up if you want to see. The reagents used for nitration of benzene, it's concentrated nitric acid and concentrated sulfuric acid. That was quite sloppy there. Quite a lot of people missed out the concentrated and therefore lost the mark. And I've taught you an equation for the formation of NO2+. Some of you have kind of learnt an alternative version, which is perfectly okay. It's in your textbooks. I've taught you the one that I know, and that is this. And it's perfectly fine, by the way. The exam board don't mind whichever one you put down. So HNO3 plus H2SO4 gives you NO2 plus H2O plus HSO4 minus. That. Okay, there are some alternatives which are acceptable. And finally, the mechanism between two. Do we need this anymore? 2 bromomethyl. No, we don't. 2 methyl bromo propane and aqueous sodium hydroxide. First thing to spot is this is a tertiary halogenoalkane redraw. So really it had to be an SN1 mechanism if you're going to get the marks. You could get a couple if it was a perfect wrong mechanism for if you drew an SN2, but it's not really what I expect you to be doing. And you've got aqueous sodium hydroxide. Much prefer it. In fact, let's draw the hydroxide when you're drawing it like so. Alright, so the first step, because it's SN1, is just the breaking of that bond. And I'm going to draw the product carbocation beneath. Don't forget, you often have to explain the stability of the carbocation, or the importance of the stability of the carbocation, which is the reason that this mechanism takes place this way, or one of the reasons, is because the carbocation intermediate is relatively stabilised because of three methyl groups on it, which have an inductive effect which pushes electron density towards the carbocation carbon. And then the next step is to take the hydroxide, attack that carbon. Really you should be drawing from the lone pair. And you draw the products over here, so I've made a bit of a mess of this, to be honest. So you get a mark for that arrow, you get a mark for the carbocation, you get a mark for attack of the carbocation with the hydroxide, ideally coming from the lone pair of the oxygen, and you get a mark for drawing the products together. Now, I was saying at the start, I prefer it if you draw it like that rather than NaOH. You've got to be really careful because some people draw things like NaOH like this, or NaOH, and that would always lose a mark because this line here represents a covalent bond, which of course it's not, it's an ionic compound. So don't draw sodium hydroxide with a covalent bond, please, otherwise you're never going to get any marks. Just leave the sodium out altogether. Okay. You don't need it either in the product here or in the reactant. Job done, finished.